The Gauss law that we studied in electrostatics is analogous to the Ampere's law. Gauss law establishes a relation between the integral of the normal component of an electric field over a closed surface and the net charge enclosed by the closed surface, and helps in the calculation of the electric field intensity at a given point. Mathematically, it is represented as the integral over a closed surface S, E dot ds is equal to Q by epsilon naught, where epsilon naught is the permittivity of free space. Ampere's law gives a relation between the integral of the tangential component of a magnetic field at points on a closed curve and the net current through the area bounded by the curve, and helps in the calculation of the magnetic induction at a given point. Ampere's law states that integral over a closed curve C B dot dl is equal to mu naught I, where mu naught is the magnetic permeability of free space. The Gauss law aims to calculate the electric field, whereas the Ampere's law aims to calculate the magnetic field. Let us discuss the Ampere's law in more detail. We shall discuss why we should consider only the tangential component of a magnetic field and neglect its normal component. We shall also discuss the sign convention for the currents to calculate the net current through an area enclosed by an Amperian loop. Let us consider a conducting wire carrying a current I. Consider a closed loop of any arbitrary shape around the conducting wire in a plane perpendicular to the plane of the conducting wire. Consider a small element of length dl on the boundary of the closed loop. B is the magnetic induction due to the current I passing through the conductor at the small element of the closed loop. The direction of the magnetic field at the small element can be found by using the right-hand thumb rule. On resolving the magnetic field into its two components, the component of the magnetic field along the length of the small element of the closed loop is called the tangential component of the magnetic field. Let it be Bt. And the component of the magnetic field perpendicular to the length of the small element of the closed loop is called the normal component of the magnetic field. Let it be Bn. The scalar product of the tangential component of the magnetic field and the length of the small element of the closed loop is Bt dot dl is equal to Bt dl cos theta. Since the angle theta between the tangential component of the magnetic field and the length of the small element of the closed loop is 0 degrees and cos 0 is equal to 1, Bt dot dl is equal to Bt dl. The scalar product of the normal component of the magnetic field and the length of the small element of the closed loop is Bn dot dl is equal to Bn dl cos theta. Since the angle theta between the normal component of the magnetic field and the length of the small element of the closed loop is 90 degrees and cos 90 is equal to 0, Bn dot dl is equal to 0. Hence, the normal component of the magnetic field can be ignored. According to Ampere's law, integral over the closed curve C Bt dot dl is equal to mu naught times the total current enclosed by the closed loop, I. That is, integral over the closed curve C Bt dl is equal to mu naught times I. This closed curve is called the Amperian loop. While using Ampere's law, sign conventions are also involved. Giving an arrow mark on the arbitrary shape of the curve assigns a sense to the curve. Now we shall discuss the rules to assign sign to the direction of a current in an Amperian loop. Let us consider multiple current-carrying conductors enclosed by an Amperian loop. Using the right-hand thumb rule, we can assign signs to these currents depending on the direction of their flow. Curl the fingers of the right hand along the arrow mark on the curve. Then, the currents along the direction of the stretched thumb are considered as positive, and the currents in the direction opposite to that of the stretched thumb are considered as negative. In this example, the currents I1, I3, and I5 are positive, and the currents I2 and I4 are negative. Let us now derive the expression for magnetic induction due to an infinite long straight current carrying conductor. Using Ampere's law. Consider an infinite long straight conductor carrying a current I. The magnetic field around the current carrying conductor is in the shape of circular loops. Consider an Amperian loop around the conductor in the shape of a circle. Let R be the radius of the Amperian loop. Consider a small element, dl, on the Amperian loop. The magnetic induction, B, at the small element of the Amperian loop, due to the current passing through the conductor, is tangential to the small element of the Amperian loop. We know that the scalar product of magnetic induction and the length of the small element of the Amperian loop, B dot dl, is equal to B dl cos theta. Since the magnetic field and the length of the small element of the Amperian loop are in the same direction, the angle between them is 0 degrees. Cos 0 is equal to 1. Therefore, B dot dl is equal to B dl. Let this be equation 1. According to Ampere's law, integral over the closed curve C, B dot dl is equal to mu naught I. On substituting equation 1 in the Ampere's law, we get integral over the closed curve C, B dl is equal to mu naught I. Let this be equation 2. Since the perpendicular distance r from the conductor to the periphery of the Amperian loop is constant, the magnetic induction B at every point on the boundary of the Amperian loop is constant. Then, equation 2 can be written as B into integral over the closed curve C, dl is equal to mu naught I. Let this be equation 3. The integral over the closed curve C, dl is equal to the total length of the Amperian loop, which is equal to the circumference of the circle. That is, integral over the closed curve C, dl is equal to 2 pi r. Let this be equation 4. Substituting equation 4 in equation 3, we get B into 2 pi r is equal to mu naught I. Then, B is equal to mu naught I by 2 pi r. Let this be equation 5. Thus, the magnetic induction at a distance r from the infinite straight current carrying conductor, B is equal to mu naught I by 2 pi r. Even if the conductor is infinitely long, the magnetic induction due to the conducting wire is finite. The magnetic induction is directly proportional to the current passing through the conducting wire. That is, B is directly proportional to I. The magnetic induction is also inversely proportional to the distance from the conducting wire. That is, B is inversely proportional to R. For a constant current, the magnetic field depends on R and possesses cylindrical symmetry. As the magnitude of the magnetic induction at every point on each concentric circular loop is constant. The direction of the magnetic field can be determined by using the right-hand thumb rule. Imagine a straight conducting wire held in your right hand. Stretch the thumb in the direction of the current. The curl of the fingers around the conductor represent the direction of the magnetic field. Let us now compare the Ampere's law and the Biot-Savart's law. The Ampere's law and the Biot-Savart's law help us to calculate the magnetic field due to the current passing through a conductor. The Biot-Savart's law is similar to Coulomb's law for electrostatics. According to the Coulomb's law, electric field strength at a point due to a charge is inversely proportional to the square of the distance from the charge to the point, that is, E is inversely proportional to R square. According to the Biot-Savart's law, the magnetic induction at a point due to the current-carrying conductor is inversely proportional to the square of the distance from the conductor to the point, that is, B is inversely proportional to R square. The Ampere's law is similar to the Gauss law for electrostatics. According to the Gauss law, integral over the closed surface S E dot ds is equal to Q by epsilon naught. According to the Ampere's law, integral over the closed curve C B dot dl is equal to mu naught I. Only when the symmetry of the situation allows us to take B outside the integral B dot dl, we can calculate the magnetic induction using the Ampere's law. It offers the most convenient way of calculating the magnetic induction, like in the case of a straight current carrying conductor. Otherwise, we have to apply the Biot-Savart's law to calculate the magnetic induction, like in the case of a circular current carrying conductor or of any shape. Now, let us discuss the application of Ampere's law to calculate the magnetic induction at a point inside and outside a straight current carrying conductor. Let us consider a straight conductor of uniform circular cross-section with radius A, carrying a current I, which is uniformly distributed across the cross-section. Let us consider the direction of the current as coming out from the plane of the screen. Let us consider a point P outside the conducting wire at a distance R from the center of the cross-section of the wire. Consider an Amperian loop in the shape of a circle, concentric with the cross-section of the wire and having radius R, such that R is greater than A. The current enclosed by the Amperian loop is I, and the total length of the Amperian loop is equal to 2 pi R. That is, integral over the closed curve C dl is equal to 2 pi R. Let this be equation 6. From Ampere's circuital law, integral over the closed curve C B dot dl is equal to mu naught I. Let this be equation 7. Since the magnetic field at any point on the Amperian loop is in the direction of the tangent to the Amperian loop at that point, B dot dl can be written as BDL. Then, equation 7 can be written as integral over the closed curve C BDL is equal to mu naught I. Let this be equation 8. The magnetic induction at every point on the Amperian loop is constant. Then, B into integral over the closed curve C dl is equal to mu naught I. Let this be equation 9. Substituting equation 6 in equation 9, we arrive at the relation B into 2 pi R is equal to mu naught I. On rearranging the terms, we get the magnetic induction at the point P due to the current carrying wire B is equal to mu naught I by 2 pi r. Let this be equation 10. When the current passing through the conductor is constant, B is inversely proportional to R. Now, let us consider another case, in which the point P is inside the conductor at a distance r from the center of the cross-section of the wire. Consider an Amperian loop in the shape of a circle, concentric with the cross-section of the wire and having radius r such that r is less than a. Total length of the Amperian loop is equal to 2 pi r. That is, integral over the closed curve C, dl is equal to 2 pi r. Let this be equation 11. The steady current passing through the conductor is I. Then the current distribution per unit area of cross-section of the conductor is equal to I by pi a square, where a is the radius of the conducting wire. Let this be equation 12. Then the total current enclosed by the Amperian loop, IE, is equal to I by pi a square into pi r square, where r is the radius of the Amperian loop. Let this be equation 13. From Ampere's law, integral over the closed curve C, B dot dl is equal to mu naught IE, where IE is the current enclosed by the Amperian loop. Let this be equation 14. Since the magnetic field at any point on the Amperian loop is in the direction of the tangent to the Amperian loop at that point, B dot dl can be written as BDL. Then, equation 14 can be written as integral over the closed curve C, BDL is equal to mu naught IE. Let this be equation 15. The magnetic induction at every point on the Amperian loop is constant. Then, B into integral over the closed curve C, dl is equal to mu naught IE. Let this be equation 16. Substituting equations 11 and 13 in equation 16, we get B into 2 pi r is equal to mu naught into I by pi a square into pi r square. On further simplification, we get B is equal to mu naught IR by pi a square. This equation shows that for all points where r is less than a, the magnetic induction B is directly proportional to r. If we plot a graph taking the distance from the current on x-axis and the magnetic field induction on y-axis, the graph is as shown. From the graph, it is clear that the magnetic induction varies linearly from the center of the cross-section of the wire to the periphery of the wire. And for all the points outside the conductor, the magnetic induction decreases with the increase in the distance from the center of the wire. A solenoid is a long wire wound in the shape of a helix. The solenoid is coated with insulated material such that the adjacent loops are insulated from each other. Let us now consider the given solenoid to have a length L and a radius of its circular loop R. Generally, the length of a solenoid is much greater than its radius. That is, L is much greater than R. Now let I be the current passing through the solenoid. This current-carrying solenoid produces a magnetic field. This can be easily understood by considering the field due to the individual circular loops. Let us now take a look at the cross-section view of the circular loops of the solenoid in the plane of the screen. Here, the dot mark with a concentric circle around it indicates the direction of current coming out from the plane of the screen, and the cross mark with a concentric circle around it indicates the direction of current going into the plane of the screen. Consider two adjacent circular loops placed coaxially and carrying equal currents. The magnetic fields at the midpoint between the peripheries of these two adjacent current-carrying circular loops are equal in magnitude but opposite in direction. Thus, the resultant magnetic field at the midpoint between the peripheries of the two adjacent coils is 0. The magnetic field inside the solenoid, either along the axis of the solenoid or along the radii closer to the axis, is uniform. To calculate the magnetic induction due to the current-carrying solenoid by using Ampere's law, consider an Amperian loop PQRS in the shape of a rectangle as shown. The PQ segment of the rectangular loop is along the axis of the solenoid and represents its length, denoted by h. Thus, the lengths PQ and RS are both equal to h. The segments QR and SP represent the breadth of the rectangular loop. According to Ampere's circuital law, integral over the closed loop B dot dl is equal to mu naught, i.e., the current enclosed by the Amperian loop. Let this be equation 1. This can be calculated by considering the magnetic fields along the lines PQ, QR, RS, and SP of the Amperian loop. That is, integral over the closed loop B dot dl is equal to integral over PQ B dot dl plus integral over QR B dot dl plus integral over RS B dot dl plus integral over SP B dot dl, which is equal to mu naught IE. Let this be equation 2. The line segments QR and SP of the Amperian rectangular loop are perpendicular to the magnetic field. Thus, the angle between the direction of current through these segments of the loop and the direction of the magnetic field is 90 degrees. As cos 90 degrees is equal to 0, B dot dl is equal to B dl cos 90 degrees, which is equal to 0. Hence, integral over QR B dot dl is equal to integral over SP B dot dl is equal to 0. Let this be equation 3. The magnetic induction outside the solenoid is very less, and it becomes almost 0 as we move away from the solenoid. Hence, the magnetic induction outside the solenoid is assumed to be 0. Alternately, if we choose the Amperian rectangular loop such that its breadth is much greater than its length, the distance of the line segment RS becomes very far from the solenoid. Hence, the magnetic induction due to the solenoid at the segment RS is 0. Thus, integral over RS B dot dl is also equal to 0. Let this be equation 4. On substituting the equations 3 and 4 in the equation 2, we get integral over PQ B dot dl is equal to mu naught IE. Inside the solenoid, the line segment PQ of the loop is parallel to the magnetic field due to the solenoid. Thus, the angle between the line segment PQ and the magnetic field is 0 degrees and cos 0 degrees is equal to 1. Hence, the integral over PQ B dot dl is equal to integral over PQ BdL, which is equal to mu naught IE. Since the magnetic field inside the solenoid is uniform, which is a constant, we can write the equation as B into integral over PQ dL is equal to mu naught IE. As the length of the segment PQ is h, the equation can be written as B into h is equal to mu naught IE. Let this be equation 5. Let n be the total number of turns on the solenoid, and L be the length of the solenoid. Then, the number of turns per unit length n is equal to n by L. The number of turns included in the Amperian loop of length h is equal to number of turns per unit length into length of the Amperian loop. That is, NAL is equal to n into h. Let this be equation 6. The current through one turn of the solenoid is I. It is the same current through all the turns of the solenoid. Hence, the total current enclosed by the Amperian loop, IE, is equal to the number of turns of the solenoid bounded by the Amperian loop, NAL, into I. Let this be equation 7. On substituting equation 6 in equation 7, we get the total current enclosed by the Amperian loop, IE, is equal to NHI. Let this be equation 8. Substitute the value of IE from equation 8 in equation 5. We get B into H is equal to mu naught into NHI. This implies that the magnetic induction due to solenoid B is equal to mu naught Ni. Let this be equation 9. The direction of the magnetic field can be found using the right-hand thumb rule. From equation 9, it is clear that the magnitude of the magnetic field, B, is proportional to I. That is, the magnetic induction inside the solenoid is directly proportional to the current through the solenoid, when the number of loops of the solenoid is constant. Thus, as the magnitude of the current passing through the solenoid increases, the magnetic induction inside the solenoid also increases. B is proportional to N. That is, the magnetic induction is directly proportional to the number of turns per unit length of the solenoid, provided the current through the solenoid is constant. When the conducting wire is wound such that the turns are closely spaced, the number of turns per unit length increases. In this case, the strength of the magnetic field inside the solenoid also increases. The magnetic field inside the solenoid also depends on the nature of the material placed in the core of the solenoid. When a magnetic substance, like soft iron, is placed in the core of the solenoid, then the strength of the magnetic field inside the solenoid increases. This is due to the property of soft iron to allow a magnetic field to pass through it. Now let us discuss the application of Ampere's circuital law in the case of a toroid. A toroid is a hollow circular ring on which a large number of turns of an insulated conducting wire are closely wound. In other words, a toroid is a solenoid bent in a circular shape. Let I be the current passing through the toroid. For convenience, we ignore the ends of the wire of the toroid through which the current enters and leaves the coil, and consider the toroid wire as continuous without any endpoints. To calculate the magnetic induction due to the current-carrying toroid, let us consider 3 concentric circular Amperian loops, represented by 1, 2, and 3 around the toroid as shown, with their centers at the center of the toroid. The area enclosed by loop 1 lies in the interior open space of the toroid. Hence, it does not cut any turn of the toroid. The periphery of the area enclosed by loop 2 passes through the inside of the toroid such that each turn of the toroid is cut by the area of loop 2 once. On the other hand, the area bound by loop 3 extends over to the exterior space of the toroid. Hence, the area bound by loop 3 cuts each turn of the toroid twice. Let R1, R2, and R3 be the radii of the 3 Amperian circular loops respectively. Let B1, B2, and B3 be the magnetic inductions due to currents I1, I2, and I3 enclosed by the Amperian loops 1, 2, and 3 respectively. Consider the Amperian loop 1. According to Ampere's circuital law, integral over the closed loop 1 B1 dot dl is equal to mu naught I1. As the area bound by loop 1 does not cut any turn of the toroid, the net current enclosed by the Amperian loop 1 is I1 is equal to 0. Then, integral over the closed loop 1 B1 dot dl is equal to mu naught into 0. Hence, the magnetic induction due to the current enclosed by the Amperian loop 1 B1 is equal to 0. Now consider the Amperian loop 3. According to Ampere's law, integral over the closed loop 3 B3 dot dl is equal to mu naught I3. As the area bound by loop 3 cuts each turn of the toroid twice, each outer part of the turn in loop 3 has a corresponding inner part turn in the loop. Hence, the amount of current coming out from the plane of the screen is equal to the amount of current entering into the plane of the screen. Thus, the net current enclosed by loop 3 is equal to 0. Then, the integral over the closed loop 3 B3 dot dl is equal to mu naught into 0. Hence, the magnetic induction due to the current enclosed by the Amperian loop 3 B3 is equal to 0. Now consider the Amperian loop 2. According to Ampere's law, integral over the closed loop 2 B2 dot dl is equal to mu naught I2. For simplicity, let us assume that the radius of the Amperian loop 2 as R and magnetic induction B2 as B. Thus, the equation for the integral over the closed loop 2 is modified to B dot dl is equal to mu naught I2. In the core of the toroid, the length dl of the infinitesimal segment of the Amperian loop is in the direction of the magnetic field. Hence, the angle between them is 0. As cos 0 is 1, we get B dot dl equal to B dl cos 0, which is equal to B dl. Since the magnitude of the magnetic induction is constant inside the toroid, this equation can be represented as B integral over the closed loop 2 dl is equal to mu naught I2. The total length of the Amperian loop 2 is its circumference, which is equal to 2 pi r. Thus, B into 2 pi r is equal to mu naught I2. Let n be the total number of turns in the toroid. Therefore, the total current enclosed by the Amperian loop 2, I2, is equal to Ni. Substituting the value of I2 in the expression and simplifying, we get the magnetic induction due to the current carrying toroid B is equal to mu naught Ni by 2 pi r. Note that the magnetic induction is inversely proportional to the radius of the toroid, provided the other quantities in the expression are constant. That is, as the radius of the toroid increases, the magnetic induction decreases. Magnetic induction is directly proportional to the current passing through the toroid, when the other quantities in the expression are constant. Hence, as the current passing through the toroid increases, the magnetic induction increases. Magnetic induction is directly proportional to the number of turns of the toroid when the other quantities in the expression are constant. If we increase the number of turns per unit length of the toroid by winding the turns closer to each other, the magnetic induction due to the toroid also increases. Let us consider a straight current-carrying conductor, XY, of infinite length. And like any current-carrying conductor, it produces a magnetic field around it. Now we introduce another straight current-carrying conductor, PQ, of infinite length above XY. This new conductor is in the external magnetic field of the conductor XY such that PQ is parallel to XY. Now, we will notice that due to the external magnetic field of the conductor XY, the conductor PQ experiences a magnetic force. This implies that there will also be a force on XY due to PQ in accordance with Newton's third law. From this, we can understand that two straight parallel current-carrying conductors placed close to each other exert force on each other, because they lie in the magnetic fields produced by one another. Now let us find the force of attraction between the conductors carrying currents in the same direction. Let us first find the force exerted by conductor XY on conductor PQ. Let the currents passing through the two straight conductors XY and PQ be I1 and I2 respectively. Let the current through both the conductors be in the same direction. Let D be the distance between them. The magnitude of the magnetic field induction is constant at all the points, which are at equal distances from the conductor. Let the magnitude of magnetic induction due to current in XY at PQ be B1. The direction of the magnetic induction B1 at PQ can be found by using the right-hand rule. If we place a stretched right hand such that the thumb indicates the direction of current in XY, the direction of curl of the four fingers of the hand indicates the direction of the magnetic field due to the current in XY as shown. The magnitude of magnetic induction at any point along conductor PQ due to current in conductor XY is B1 is equal to mu naught I1 by 2 pi d. Let this be equation 1. The magnitude of the force experienced by a segment of length L of the conductor PQ due to the magnetic field produced by the conductor XY is F21 is equal to B1 I2 L sin theta, where theta is the angle between the direction of the magnetic field B1 and the current in the conductor PQ. Let this be equation 2. Here, theta is equal to 90 degrees and sin 90 is equal to 1. Therefore, the force acting on the segment of the conductor PQ of length L due to the conductor XY is equal to F21 is equal to B1 I2L. Let this be equation 3. On substituting the value of B1 from equation 1 in equation 3, we arrive at the expression F21 is equal to mu naught I1 I2 by 2 pi d into L. Let this be equation 4. The direction of the force experienced by conductor PQ due to the magnetic field produced by the conductor XY can be found using Fleming's left-hand rule. According to Fleming's left-hand rule, stretch the 3 fingers, thumb, forefinger, and central finger of your left hand mutually perpendicular to each other. If the central finger represents the direction of the current and the forefinger represents the direction of the magnetic field, then the direction of the thumb represents the direction of the force acting on the current-carrying conductor. Thus, the force F21 is directed towards the conductor XY. As discussed earlier, the current-carrying conductor XY experiences the same force due to the magnetic field produced by the current I2 in the conductor PQ. This is in line with Newton's third law. The magnitude of the magnetic induction due to the current-carrying conductor PQ is B2 is equal to mu naught I2 by 2 pi d. Let this be equation 5. The direction of the magnetic induction due to current I2 through PQ can be found by the right-hand rule. The magnitude of the force acting on the segment conductor XY of length L due to the magnetic field produced by the current through conductor PQ is F12 is equal to B2I1L, which is equal to mu naught I1 I2 by 2 pi d into L. Let this be equation 6. The direction of this force can be found by using Fleming's left-hand rule, and the force acting on the conductor XY is towards the conductor PQ. When you compare equations 4 and 6, you realize the two forces, F21 and F12, are equal in magnitude but act in opposite directions towards each other. Hence, if the currents in the two parallel straight current-carrying conductors are in the same direction, the two conductors attract each other. On the other hand, if the currents in the two straight parallel conducting wires are in opposite directions, then the forces exerted by the conductors on each other are equal in magnitude but repulsive in nature. Thus, they repel each other. Thus, the magnitude of the force F between two parallel conductors of infinite length L, separated by distance d, carrying current I1 and I2 respectively in them, is equal to mu naught I1 I2 by 2 pi d into L. Let this be equation 7. Therefore, the force acting per unit length of the conductor F is equal to F by L, which is equal to mu naught I1 I2 by 2 pi d. Let this be equation 8. Using this expression for force per unit length, let us now define the SI unit, ampere. Let the distance of separation between the conductors D be equal to 1 unit, which is 1 meter. Let the current through the two conductors be equal to 1 unit, which is 1 ampere. Then, the force per unit length becomes mu naught by 2 pi. On substituting the value of mu naught, which is 4 pi into 10 power minus 7, we get F equal to 2 into 10 power minus 7 Newton per meter. Thus, if two straight parallel conductors of infinite length, separated by a distance of 1 meter in vacuum, exert a force of 2 into 10 power minus 7 Newton per meter on each other, then the current passing through each conductor is said to be 1 ampere. The SI unit of charge is also defined from the unit of current. If a constant current of 1 ampere passes through the cross-section of a conductor in 1 second, then the charge passing through it is said to be 1 coulomb. Practically, it is not possible to demonstrate the force between the two current-carrying conductors we discussed, as the effects of magnetism are generally smaller than the effects of electricity. To study a similar effect of force, as between two current-carrying conductors, we replace the straight long wires with a coil of suitable dimensions and number of turns. We refer to this as Roget's spiral. Consider a soft spring with a natural frequency of oscillation equal to 1 Hz or with a natural time period of oscillation as 1 second, suspended vertically from a rigid support. Take some mercury in a bowl and place it exactly below the suspended spring in such a way that the lower end of the spring is just in contact with the surface of the mercury. Take a DC current source, connect one of the terminals to the top of the spring, and the other terminal is connected to a switch. And then it is dipped in the mercury taken in the bowl, so that the circuit gets closed. When the circuit is switched on, due to a constant current passing through the adjacent turns of the spring, the coils attract each other, and the spring comes out from the mercury and the circuit is broken. As a natural action, the spring relaxes and again comes in contact with the surface of the mercury. Then the circuit gets closed and again the adjacent loops attract due to the current in the coil. The force of attraction between two adjacent loops in the coil is similar to the force of attraction between two parallel current-carrying conductors, when the direction of current through them is the same. While doing this activity, we should take care to keep the face away from the mercury vapors, because mercury vapors are poisonous. We know that a current-carrying circular loop produces a magnetic field. This magnetic field is similar to the magnetic field due to a magnetic dipole. This magnetic field is also similar to the electric field due to an electric dipole. Now, let us study the magnetic induction at a point on the axis of the circular current-carrying loop and compare it with the magnetic induction at a point on the axial line of a magnetic dipole. Let us compare this magnetic field with the electric field strength at a point on the axial line of an electric dipole. We have learnt earlier that the magnitude of the net magnetic induction at a point on the axis of the circular loop, at a distance x from the center of the circular loop, BA is equal to mu naught IR square by 2 into R square plus X square whole power 3 by 2. Let this be equation 1. The direction of the field is along the axis of the circular loop. When the distance from the center of the loop to the point P is far greater than the radius of the circular loop, that is, X is far greater than R, the term R square in the denominator may be neglected. Now the equation 1 is transformed to BA is equal to mu naught IR square by 2x cube. On multiplying with pi in the numerator and the denominator, we get BA is equal to mu naught by 2 pi into I into pi R square by x cube. We know that the area of a circular loop, A is equal to pi R square. On substituting A for pi R square in the equation, the magnetic induction can now be written as BA is equal to mu naught by 2 pi into IA by x cube. We have learnt earlier that magnetic moment of a current-carrying loop is the product of the current passing through the loop and area of the loop, that is, M is equal to IA. On substituting the magnetic moment, we get the magnetic induction at the point P on the axis of the circular current loop, BA is equal to mu naught by 2 pi into M by x cube. By multiplying with 2 in the numerator and the denominator, we can write the magnetic induction at a point P on the axis of the circular loop as BA is equal to mu naught by 4 pi into 2M by x cube. Let this be equation 2. Now, let us compare the magnetic induction along the axial line of the circular current loop with the field strengths of the magnetic dipole and the electric dipole at points along their axial lines. We know that the magnetic induction along the axis of the circular current loop, BA, is equal to mu naught by 4 pi into 2M by x cube. We know that the magnetic induction at a point P on the axial line, at a distance x from the center of magnetic dipole, BA is equal to mu naught by 4 pi into 2M by x cube, where M is the magnetic moment of the dipole. We also know that the electric field intensity at a point P on the axial line at a distance x from the center of electric dipole, EA, is equal to 1 by 4 pi epsilon naught into 2 PE by x cube, where PE is the moment for the electric dipole. Let this be equation 3. The magnetic induction at a point P on the axis of a circular current loop is exactly the same as the magnetic induction at a point P on the axial line of a magnetic dipole. Compare equations 2 and 3 to notice that mu naught is analogous to 1 by epsilon naught. This depends on the medium where the electric dipole or the magnetic dipole is placed. M is analogous to PE. That is, the magnetic dipole moment is similar to the electric dipole moment. Also, BA is similar to EA. That is, the magnetic induction is similar to the electric field intensity. Now let us compare the magnetic induction at a point on the equatorial line of a magnetic dipole with the electric field strength on the equatorial line of an electric dipole. Using the comparison, let us arrive at an expression for magnetic induction at a distant point on the plane of a current-carrying circular loop. We know that the electric field intensity on the equatorial line of an electric dipole at a point which is at a distance x from the center of the electric dipole, EE, is equal to 1 by 4 pi epsilon naught into PE by x cube. Let this be equation 4. Here, the distance x of the point is much greater than half the length of the electric dipole. Similarly, in case of a magnetic dipole, the magnetic induction at a point on the equatorial line at a point which is at a distance x from the center of the magnetic dipole is BE is equal to mu naught by 4 pi into M by x cube. Let this be equation 5. Here the distance x of the point is much greater than half the length of the magnetic dipole. Let us make use of the similarity in the relations we have arrived at. While we mapped the magnetic induction at a point on the equatorial line of a magnetic dipole and electric field strength at a point on the equatorial line of an electric dipole. Mu naught is analogous to 1 by epsilon naught. M is analogous to PE. That is, the magnetic dipole moment is similar to the electric dipole moment. and BE is analogous to EE. That is, the magnetic induction is similar to the electric field intensity. Substituting these similar values in equation 4, we arrive at the magnetic induction at a distant point P on the line which is in the plane of the circular loop as BE is equal to mu naught by 4 pi into m by x cube. Here too, the distance x of the point is much greater than the radius of the circular loop. Observe that the magnetic field produced by a current carrying circular loop is similar to the magnetic field due to the magnetic dipole at large distances. Such a dipole is referred to as a point magnetic dipole. A current-carrying conductor placed in a uniform magnetic field experiences some force. The magnitude of this force is determined by using the formula F is equal to BIL sin theta, where theta is the angle between the direction of the magnetic field and the direction of current. The direction of the force acting on the conductor can be determined by using Fleming's left-hand rule. According to the rule, when we stretch the thumb, the index finger and the middle finger on the left hand in 3 mutually perpendicular directions, if the middle finger indicates the direction of current in the conductor, the index finger indicates the direction of the uniform external magnetic field. Then, the thumb indicates the direction of the force on the conductor. Now, let us discuss the forces acting on a rectangular current carrying loop when it is placed in a uniform magnetic field. Consider a rectangular loop PQRS of length L and breadth B placed in a uniform magnetic field in such a way that the plane of the loop is parallel to the magnetic field. Connect the rectangular loop to a battery as shown, such that the current in the loop is along the direction PQRS. Let B be the magnetic induction of the uniform magnetic field between the two magnets, and I be the constant current passing through the rectangular loop. To simplify the understanding of the topic, we neglect the ends of the loop from where the current enters and leaves the loop. The magnetic field exerts some force on the arms of the current-carrying rectangular loop. The direction of current in the arm PQ of the loop is perpendicular to the direction of magnetic field. Sin 90 is equal to 1. Hence, the magnitude of the force acting on the arm PQ of the rectangular loop due to the magnetic induction B is F1 is equal to BIL sin 90, which is equal to BIL, where L is the length of the arm PQ. Let this be equation 1. Here, the direction of the force is determined by using Fleming's left-hand rule. Stretch the 3 fingers of left hand in 3 mutually perpendicular directions. Here, the direction of the magnetic field is from north to south, represented by the index finger of the left hand. The direction of current is from P to Q of the rectangular loop, represented by middle finger, and the direction of thumb represents the direction of force acting on the arm PQ of the loop. That is, the force is acting downward with respect to the plane of the loop. The direction of the current in the arm QR is parallel to the direction of the external magnetic field. This implies that the angle between the direction of the current in QR and the direction of the magnetic field is 0 degrees. Sin 0 is equal to 0. Hence, the magnitude of the force acting on the arm QR of the rectangular loop due to the magnetic induction B is F2 is equal to 0. Let this be equation 2. The angle between the direction of the current in RS part of the loop and the direction of the magnetic field is 90 degrees. Sin 90 is equal to 1. Hence, the magnitude of the force acting on the arm RS of the rectangular loop due to the magnetic induction B is F3 is equal to BIL. Let this be equation 3. Here, using Fleming's left-hand rule, we find that the force acts upwards with respect to the plane of the loop. The angle between the direction of current passing through the arm SP of the loop and the direction of the magnetic field is 180 degrees. Sin 180 degrees is equal to 0. Hence, the magnitude of the force acting on the arm SP of the rectangular loop due to the magnetic induction B is F4 is equal to 0. Let this be equation 4. We observe from the equations that the magnitudes of F1 and F3 are equal. As they act on the loop in opposite directions, they are unlike forces. Hence, the net force acting on the body is 0. As the two forces F1 and F3 are non-collinear and are separated by the perpendicular distance B, which is equal to the breadth of the rectangular loop, they result in turning the loop. These two forces cause the rectangular loop to rotate about an axis that lies in the plane of the loop, parallel to its length and passing through its center. Thus, the axis of rotation of the loop passes through the midpoints of QR and SP. The magnitude of the torque TO1 due to F1 is equal to the product of F1 and the perpendicular distance between the point of application of F1 and the axis of rotation. This gives TO1 is equal to F1 into half of B. Similarly, the magnitude of torque TO3 due to F3 is equal to F3 into half of B. The net torque on the loop TO is equal to the sum of TO1 and TO3, which is equal to F1 into B by 2 plus F3 into B by 2. But F1 is equal to F3 and both are equal to BIL. Then, TO is equal to BIL into B by 2 plus BIL into B by 2, which is equal to BI into LB. As L into B is equal to the area of the rectangular loop A, we can denote the torque acting on the rectangular current loop TO is equal to BIA. The net torque on the loop tends to rotate it in the anti-clockwise direction when viewed from SP side of the loop. We know that torque is a vector. Hence, the expression for torque on the rectangular current-carrying loop placed in the external magnetic field can be represented using vectors. We know that magnetic induction B is a vector. We now assume another vector A called the area vector. The direction of the area vector is given by right-hand rule. If the right hand is stretched and the four fingers of the hand curl in the direction of the current in the loop, then the thumb, which is extended out, indicates the direction of the area vector. Hence, the direction of the area vector in this case points into the loop when we observe it from top, such that the current in the loop is in the clockwise direction. If theta is the angle between the two vectors, then the torque on the loop is given by the cross product IA cross B, whose magnitude is equal to IAB sin theta. We now define a new vector, magnetic moment, denoted by M, which is equal to the product of I and A. Thus, the direction of M is the same as that of the area vector, and its SI unit is ampere meter square. Hence, torque on the current-carrying rectangular loop is given by the expression TO is equal to M cross B, and hence, the magnitude of the torque on the loop is given by MB sin theta. In this case, the angle between the magnetic moment and the magnetic induction is 90 degrees. As sine 90 is equal to 1, the torque on the loop is the maximum. Now let us consider another case where the magnetic moment makes an angle theta other than 90 degrees with the direction of the magnetic field. That is, the angle between the directions of the area vector and the magnetic field is other than 90 degrees. When the current passes through the rectangular loop, the magnetic field exerts some force on the sides of the rectangular loop as discussed earlier. Here too, the angle between the direction of current through PQ and the direction of magnetic field is 90 degrees. Hence, the force acting on the arm PQ of the rectangular loop due to the magnetic induction B is F1' is equal to BIL. Let this be equation 5. Here, using Fleming's left-hand rule, we find that the force acts downwards in a direction perpendicular to the plane containing B and I. In the case of arm QR, the length of the arm QR is not perpendicular to the direction of the magnetic field. Area vector makes an angle theta with the magnetic field. Hence, the angle between the magnetic field and the current through QR is 90 minus theta. Then, the force on QR, part of the loop due to the magnetic field, is F2' is equal to BIB sine 90 minus theta, which is equal to BIB cos theta. Let this be equation 6. The direction of force F2' is obtained by using the right-hand rule. When the four fingers of a stretched right hand curl from the direction of current in QR towards the direction of magnetic induction B, the thumb indicates the direction of the force on QR. Thus, the force F2' acts perpendicular to the plane containing I and B, outward of the loop along its axis of rotation. The direction of current through the arm RS of the loop is perpendicular to the direction of magnetic field. Then, the force acting on the arm RS of the rectangular loop due to the magnetic induction B is F3' is equal to BIL. Let this be equation 7. Using Fleming's left-hand rule, we find that the force acts upward in a direction perpendicular to the plane containing current and magnetic field. The direction of current through the arm SP of the loop makes an angle 90 minus theta with the direction of the magnetic field. Then, the force acting on the SP due to the magnetic field B is F4' is equal to BIB sine 90 minus theta, which is equal to BIB cos theta. Let this be equation 8. The direction of force F4' is obtained by using right-hand rule. When the four fingers of a stretched right hand curl from the direction of current in SP towards the direction of magnetic induction B, the thumb indicates the direction of the force on SP. Thus, the force F4' acts perpendicular to the plane containing I and B outward of the loop along its axis of rotation. We observe that the forces F2' and F4', which are equal in magnitude, act along the same line, that is, along the axis of rotation. Hence, they are collinear. But they are unlike as they act in directions opposite to each other. Hence, these two forces cancel each other and their resultant is 0. Thus, these two forces do not constitute torque. On the other hand, the forces F1' and F3', which are equal in magnitude, act in opposite directions to each other and are not collinear. Therefore, the resultant of these two forces constitutes torque on the loop. The net torque acting on the loop tends to rotate it in the anti-clockwise direction when viewed from PS. The magnitude of torque due to F1' is equal to the product of force and perpendicular distance between F1' and the axis of rotation of the loop. Let D be the perpendicular distance between the force F1' and the axis of rotation of the loop. As the angle between the area vector and the magnetic field is theta, from the geometry of the figure, the perpendicular distance D between the force F1' and the axis is equal to B by 2 into cos 90 minus theta, which is equal to B by 2 into sin theta. Thus, the torque TOROID on the loop due to F1' is equal to F1' B by 2 sin theta. Similarly, the torque TO3' on the loop due to the force F3' is given by TO3' is equal to F3' B by 2 sin theta. Hence, the net torque TO' on the loop is given by the sum of TO1' and TO3'. This is equal to F1' B by 2 into sin theta plus F3' B by 2 into sin theta. But F1' is equal to F3', and both are equal to BIL. Then, TO' is equal to BIL B by 2 into sin theta plus BIL B by 2 into sin theta. Replacing L into B with area of the loop A, the torque on the loop TO' is equal to BIA sin theta. So far, we have learnt about the torque on a current-carrying rectangular loop placed in an external uniform magnetic field, in the case where the area vector makes an angle other than 90 degrees with the direction of the magnetic field. On rotation of the loop about its axis, due to the torque on it, if the angle theta tends to 0, perpendicular distance between the forces tends to 0, and this results in 0 torque on the loop. Also, while the angle reduces to 0, the value of sin theta becomes 0, which results in 0 torque on the loop. We know that, according to Bohr's atomic model, electrons in an atom revolve around the nucleus in circular orbits. The nucleus contains protons and neutrons. Protons are positively charged particles, whereas neutrons do not carry any charge. That is, they are electrically neutral. Thus, the net charge of the nucleus is positive. Electrons revolve around the nucleus in circular orbits due to the electrostatic force between the electrons in the orbits and the protons in the nucleus. Consider an electron with a charge -e revolving around the nucleus in an orbit of radius r. The charge of the nucleus is Ze, where Z is the atomic number of the element under consideration. Current due to the revolving electron I is equal to E by T, where T is the time taken by the electron to complete one revolution, called the time period of revolution. Let this be equation 1. When the electron revolves in the orbit of radius r with a constant speed v, then the time period of revolution t is equal to the circumference of the orbit by the speed of the electron v. The circumference of the orbit of radius r is equal to 2 pi r. Hence, T is equal to 2 pi r by V. Let this be equation 2. Substitute equation 2 in equation 1 to arrive at the relation I is equal to EV by 2 pi r. Let this be equation 3. We know that the magnitude of the magnetic moment M of a current-carrying loop is equal to the product of the current and the area of the loop. That is, M is equal to IA. At the atomic level, electrons or any charged particles moving in uniform circular paths have a magnetic dipole moment which is called the orbital magnetic moment. It is denoted by the Greek letter μL. The subscript L in μL indicates that the magnetic moment is of an orbital nature. Thus, the magnetic moment of the orbiting electron, μL, is equal to the product of the current I and the area of the orbit A. Let this be equation 4. The area of the orbit A is equal to pi r square. Let this be equation 5. Substituting equations 3 and 5 in equation 4 and simplifying, we get the expression for the magnetic moment of the revolving electron as μL is equal to EVR by 2. Let this be equation 6. Multiply the numerator and the denominator of equation 6 with the mass of the electron, ME. Rearranging the terms of equation 6 as shown, we get equation 7. The electron is in circular motion around the nucleus. We know that the magnitude of the angular momentum of the electron around the nucleus is given by L is equal to mEVR. Let this be equation 8. Substituting equation 8 in equation 7 and simplifying, we get the equation μL is equal to E by 2 ME into L. Let this be equation 9. In general, the magnetic moment associated with any charged particle having charge Q, mass m, and moving in uniform circular motion is called orbital magnetic moment. It is given by the expression μL is equal to Q by 2m into L, where L is the angular momentum of the charged particle. We know that the direction of the conventional current is opposite to the direction of the motion of electrons. In general, we refer to this conventional current as the electric current. Now, by using the right-hand thumb rule, we can find the direction of the magnetic momentum of the electrons. Curl the fingers of your stretched right hand along the direction of the current. The thumb then indicates the direction of the magnetic momentum. On the other hand, if we need to find the direction of the angular momentum of the electron, we use the right-hand rule again. In this case, we curl the fingers of the stretched right hand along the direction of velocity of the electron. Then, the thumb indicates the direction of the angular momentum. Thus, we find that the angular momentum of the electron and its magnetic momentum are in opposite directions. Vectorially, the relation between the magnetic momentum and angular momentum of an electron is μL is equal to minus E by 2 ME into L. The negative sign indicates that μL and L are in opposite directions. Now, let us discuss about Bohr's magneton. According to Bohr's atomic model, angular momentum of an electron revolving in an atomic orbit is quantized. That is, the angular momentum L is integral multiples of h by 2 pi. Hence, we get the equation L is equal to n into h by 2 pi, where h is the Planck's constant, whose value is 6.626 into 10 power minus 34 joules second. Let this be equation 10. Here, n can take the values 1, 2, 3, and so on. Substituting equation 10 in equation 9 and simplifying, we get the magnetic moment mu L is equal to NEH by 4 pi ME. Let this be equation 11. For an electron, the magnetic moment is minimum for n equal to 1. By substituting all the standard values of the constants in the equation and simplifying, we get the magnetic moment as 9.27 into 10 power minus 24 ampere meter square. This value is called Bohr magneton. This is also referred to as the spin magnetic moment. Now let us discuss about the gyromagnetic ratio. The ratio of the magnetic moment to the angular moment is called the gyromagnetic ratio. It is denoted by gamma. That is, gamma is equal to mu L by L. On substituting the value of mu L from equation 9 and simplifying, we get gamma is equal to E by 2me. On substituting the values of charge and mass of the electron and simplifying, we get the gyromagnetic ratio of an electron as 8.8 into 10 power 10 coulomb per kilogram. A moving coil galvanometer is used to detect the direction of current in electric circuits. It is also used to measure small magnitudes of currents and voltages in electric circuits. The moving coil galvanometer works on the principle that when a current-carrying coil is placed in a uniform external magnetic field, it experiences a torque. Let us discuss this in detail. Before discussing the work of a moving coil galvanometer, let us have a look at its essential parts. The moving coil galvanometer consists of circular-shaped magnetic poles, which create a uniform radial magnetic field. It also consists of a current-carrying coil of many turns wounded in a rectangular shape over a soft iron core. The soft iron core increases the strength of the uniform radial magnetic field. In the radial magnetic field, the plane of the coil is always parallel to the direction of the magnetic field for any orientation. Hence, the angle between the plane of the coil and the direction of the magnetic field is always 0. And the angle between the axis of the coil and the magnetic field, theta, is always 90 degrees. A spring, denoted as SP, is connected to the axis of the soft iron core. On close observation, we find that one end of the spring is connected to the axis of the soft iron core, and the other is connected to a rigid support. A pointer is connected to the axis of the soft iron core. This pointer moves over a circular scale. Now, let us discuss the working of the moving coil galvanometer. When an electric source is connected to the terminals of the rectangular coil, a torque is produced. That is, when a current passes through the rectangular coil, two equal and opposite forces acting on either side of the coil produce a couple. In our present context, we refer to this couple as the torque. As you learnt earlier, the torque acting on the coil τ is equal to BIAN sin theta, where theta is the angle between the axis of the coil and the magnetic field. Here, theta is 90 degrees. Thus, sin 90 is 1, and we have the deflecting torque acting on the coil tau equal to BIAN, where B is the strength of the uniform magnetic field, A is the area of the current carrying coil, N is the number of turns in the coil, and I is the current passing through the coil. Let this be equation 1. This deflecting torque in the coil develops an equal restoring torque in the spring in the direction opposite to that of the deflecting torque. Hence, these two torques are balanced. The restoring torque produced in the spring is tau is equal to k phi, where phi is the deflection shown by the pointer and k is the torsional spring constant, the torque per unit angle. Let this be equation 2. Equating the expressions 1 and 2, and on simplification, we get phi is equal to BAN by K into I. Let this be equation 3. The value of BAN by K is constant for any given galvanometer. Hence, phi is directly proportional to I. That is, if the current passing through the coil increases, the deflection of the pointer also increases. By passing a known value of current and measuring the corresponding deflection in the coil, phi is found. From this, the deflection per unit current is calculated, and then the circular scale above which the pointer moves is graduated. This is known as calibration of the galvanometer. The ratio phi to I gives the deflection per unit angle, which is defined to be the current sensitivity. From equation 3, phi is equal to BAN by K into I. Hence, the current sensitivity phi by I is equal to BAN by K. The current sensitivity of the galvanometer can be increased by increasing the number of turns in the coil. It can also be increased by increasing the area of the coil or by increasing the strength of the magnetic field. As we discussed in the beginning of the module, a moving coil galvanometer has some applications. Let us begin our discussion with its applications in the detection of the direction of current in a given circuit. Consider a Wheatstone bridge circuit, which we learnt earlier. In this circuit, a galvanometer is used to detect the direction of current in the bridge part of the circuit. In this arrangement, the type of the galvanometer used has 0 reading in the center of the scale. The readings on the right side of 0 are considered positive, and the readings on the left side of the 0 are considered negative. When there is no current passing through the galvanometer, it shows the reading 0. Depending on the direction of current in the circuit, the galvanometer deflects either towards the right or towards the left. For example, consider that 1 microampere current is allowed to pass through the central part of the arrangement. Then, the pointer deflects towards the right side of the 0 on the scale. if the current passes from top to bottom. The pointer deflects towards the left of 0 on the scale if the current passes in the reverse direction. Galvanometer is also used to measure small magnitudes of currents in a given circuit by connecting it in series. For simplicity, let us consider a circuit diagram where the galvanometer is denoted as G. As the galvanometer consists of the long coil, it has some resistance. We refer to this as the resistance of the galvanometer, denoted by Rg. In contrast to an ammeter, which measures even current of high magnitudes, a galvanometer is used to measure small amounts of current, such as in microampere. Why can't we use a galvanometer as an ammeter? There are two reasons. First is due to the fact that the galvanometer is a highly sensitive device. The full-scale reading on the galvanometer is in the order of microampere only. And the second is, to measure the currents in electric circuits, the galvanometer has to be connected in series. Due to the resistance of the galvanometer, it can affect the value of current in the circuit when connected. This difficulty can be overcome by connecting a small resistance, Rs, in parallel to the galvanometer. This small resistance is called as the shunt resistance. When a shunt resistance is connected in parallel to the galvanometer, most of the current passes through this shunt. Thus, the change in current in the circuit is negligible. Thus, a galvanometer can be converted into an ammeter by connecting a shunt resistance in parallel to the galvanometer. The effective resistance of the galvanometer and the shunt resistance is equal to Rg/Rs by Rg plus Rs. But the galvanometer resistance is a lot higher than the shunt resistance. That is, Rg is very large as compared to Rs. In that case, Rg plus Rs becomes approximately equal to Rg. Hence, the effective resistance becomes approximately equal to Rs. The effective resistance of the galvanometer and the shunt resistance is in series with the resistance of the rest of the circuit. Let the resistance of the rest of the circuit be denoted as Rc. Thus, the effective resistance of the total circuit is equal to Rs plus Rc. But the value of the shunt resistance is a lot lesser than the resistance of the rest of the circuit. That is, Rs is extremely small as compared to Rc. Thus, the effective resistance of the total circuit is approximately equal to Rc. That is, the resistance of the measuring device in the circuit is negligible. Thus, the galvanometer can be converted into an ammeter by connecting a shunt resistance in parallel. And the scale of this ammeter is calibrated and graduated according to the current sensitivity. The galvanometer can also be used to measure the voltage across any given part of the circuit by connecting the galvanometer in parallel with the given part of the circuit. When the galvanometer is connected in parallel, the total current in the circuit divides across the part of the circuit and across the galvanometer. The galvanometer must draw a very small current from the circuit. Otherwise, the original value of the current in the circuit will be altered. In general, the alteration in current due to the measuring device in the circuit must be negligible. It should be less than 1% of the original value. To reduce the alteration in current due to the galvanometer, a large resistance is connected in series to the galvanometer. Let the large resistance be R. R being very much greater than Rg, the current passing through the galvanometer is minimized to less than 1%. Thus, the galvanometer can be converted into voltmeter by connecting a large resistance in series with the galvanometer. The effective resistance of the galvanometer and the large resistance is equal to R plus Rg. As the resistance R is very much greater than the resistance of the galvanometer, Rg, the effective resistance is approximately equal to R. Hence, a galvanometer can be converted into a voltmeter by connecting a large resistance in series. The voltmeter is calibrated and graduated on the scale according to the voltage sensitivity. Voltage sensitivity of the voltmeter is defined as the deflection per unit voltage, denoted as phi by V. From equation 3, phi is equal to BAN by K into I. Divide with voltage V on both sides. Phi by V is equal to BAN by K into I by V. From Ohm's law, V is equal to IR. Then, I by V is equal to 1 by R. Then, the voltage sensitivity, phi by V, is equal to BAN by K into 1 by R. In the case of the conversion of a galvanometer into voltmeter, an increase in the current sensitivity, which is the ratio of phi to I, does not increase the voltage sensitivity. Let us look at this in detail. Suppose the number of turns in the coil of a galvanometer is doubled, that is, N becomes 2N. By substituting 2N in place of N and on simplification, we get the new value of phi by I as 2 phi by I. That is, the current sensitivity is doubled. We know that the resistance of a wire is directly proportional to its length. As the number of turns in the galvanometer coil is doubled, length of the wire in the coil is also doubled. Thus, N becomes 2N, which implies L becomes 2L. Thus, the effective resistance R becomes 2R. By substituting 2N and 2R in place of N and R respectively, we observe that the new value of phi by V remains the same. That is, by increasing the number of turns, current sensitivity can be increased, but the voltage sensitivity remains the same.